Okay, let's get started, and welcome to the second day of the workshop. Our first speaker is Andrew Geraci from Northwestern University, and he will tell us about the levitated sensor detector. So let's welcome.
Just start the presentation. Okay, I guess.
I assume you're not going to put viruses on it?
No, hopefully not. Okay. Is there a laser or this?
So if you use this, then the people on Zoom can also see what you're pointing.
Excellent.
And if you start pointing in the middle of the slide, it's somewhat better calibrated. That's the, yeah, exactly.
Very good. Okay. Can everyone hear okay? Yeah. Okay, thanks for to the organizers for the invitation to attend this exciting meeting. It's really exciting to see how much it's grown since the one 4 years ago in Trieste. And so I'm going to say a little bit about the work we're doing at Northwestern, developing a prototype high-frequency gravitational wave detector based on levitated particles. And so let me just start off introducing the topic of optical levitation. So this really goes back to early work in the 70s by Art Ashkin and collaborators, which has recently been recognized with a Nobel Prize. So he primarily did work with suspending particles in fluids, which really led to the field of optical tweezers, which has had a very big impact in areas like biology and biophysics. He did a little bit of work experimenting with levitating dielectric particles in vacuum in the 70s, but recently there's been a significant increase in activity in this area. And so the basic idea is you have a dielectric particle, it's a polarizable medium, and so it acquires a dipole moment due to the electric field of the laser, and that dipole moment then couples again to the electric field of the laser to give you an optical potential, which goes like the square of the electric field, and that's proportional to the laser intensity. And so if you have a focused laser beam, you have an interaction which basically tries to confine the particle at the highest intensity point of the beam or at the focus of the laser. And so it's possible to think about this if you study the motion of such a particle, if at least for a spherical particle, as sort of 3 decoupled harmonic oscillators where you can have different restoring forces according to the gradient in the optical intensity along the different axes of your laser beam. And so it's possible to trap particles in this method over quite a variety of size scales, ranging from tens of nanometers up to tens of microns. And so one of the key features here is if you do this in a really high vacuum environment, you have very little friction and dissipation acting on the particle. You can, in principle, achieve very high mechanical quality factors approaching something like 10 to the 12. And as I'll explain in a little more detail, this is a route towards getting extremely good force sensitivity. And furthermore, you can actually feed back and control the temperature of the motional temperature of the oscillations of the particle using laser feedback control, for example, or other feedback schemes. And you can actually cool the motion of the particle down quite substantially. And in fact, the state of the art is that now in a couple of different groups, people have demonstrated the ability to actually cool the particle all the way into the quantum ground state of the optical trapping potential. So in addition to exploring this kind of quantum regime for the motion of these particles, they make excellent force sensors. And one of the limitations that you have to think about if you want to consider the sensitivity is the limit due to thermal noise. And so you can really think about this in sort of an analogy with Brownian motion. If you have a dust particle that's meandering around inside of some fluid, it's getting random kicks from the molecules of the fluid, which cause it to undergo some jittering random motion. And similarly, if you have some sort of mechanical oscillator in contact with some thermal bath, you can write down the equipartition theorem from statistical mechanics and figure out there's some minimum force that one can resolve on top of those random thermal kicks due to the thermal bath. And the formula that you can get for this basically goes like the thermal energy kT times your spring constant of the oscillator times the measurement bandwidth divided by the product of the frequency and this mechanical quality factor Q which is a measure of this dissipation in the system. And so there's a significant win that one can achieve by having a very, very low friction type of environment. And so here's a case where using a laser suspended particle really gives you a significant advantage. For example, if you compare with a solid state kind of mechanical system, you typically have some sort of limitation due to clamping, surface imperfections, or internal materials losses in the material. So if you instead study the motion of a particle that's just suspended with radiation pressure, now you're very well, at least the center of mass motion of that particle is very well decoupled from the environment. So you no longer have any sort of mechanical clamping mechanism, and you're not as concerned about internal materials losses and thermoelastic dissipation and other mechanisms which would otherwise cause friction in the system. So you can look at then what sort of sensitivity one can achieve in a high vacuum environment with a levitated particle. So this is, now I've rewritten that same equation a little bit differently in terms of the gas damping coefficient, gamma, and the mass of the particle. And I'm showing the sensitivity as a function of the radius of the particle from 10 nanometer scale up to tens of microns. So this is for a respectable UHV environment about 10 minus 10 torr at room temperature. And so you can see for kind of micron-sized particles, the sensitivity here is on the order of 10 to the minus 21 newtons per root hertz, or a zeptonewton per root hertz. And so this is significantly more sensitive than sort of solid-state type sensors, for example, cantilever beams and this sort of thing. If you look closely at the right side of the plot, there's actually a deviation from this straight line. And this is due to another noise source. This is basically just due to the light scattering. So there's a finite number of photons in your laser trap, and there's Rayleigh scattering of the photons off the particle. This leads to some momentum diffusion process or heating process where the particle basically gets random kicks due to the photon recoil. And in fact, that does set some limitation on your force sensitivity. However, it's possible to really still get in this regime where you can measure this kind of zeptonewton level sensitivity. Yes?
You're probably going to say later, but maybe can you already say now how you're actually reading this out? So you're measuring these impressive accelerations, but how?
Yeah. So I'll show maybe the setup, and then we can explain in just a minute. But yeah, thanks. So first, before I describe how we read out, let me just say how we catch these particles in the first place. And so basically, we have some laser trap where we basically shake a substrate that has a deposition of these particles. It turns out you need to actually shake the substrate quite substantially to release them from the substrate due to the van der Waals interaction. So the acceleration you need to shake a nanoparticle off a surface goes like 1 over the square of the radius of the particle. So if you have something on the order of a few hundred nanometers, the accelerations you need here are something like 10 to the 7 Gs. And in fact, we measure accelerations at that level of the surface. Here's a movie showing after we shake the surface, we basically get a rain shower of these particles above where the laser trap is. And here you can see, in this case, a particle is stuck in the potential. And so this is not sped up. This is a real-time movie, or it's not slowed down. And so there's some amount of residual nitrogen in the vacuum system to provide some damping mechanism to collect the particle. Otherwise, the particle would just ballistically fly through the potential and leave. But so then you have to then remove the nitrogen to really get into the high vacuum regime to get the sensitivity you want. And so this turned out to be slightly non-trivial. Also, this was noticed back in the 70s by Art Ashkin as well, where you have to worry about instabilities due to what are known as radiometric forces or photothermal effects. And so you can think about this kind of in an analogy here with early work from Crookes, who believed erroneously that he discovered the force due to radiation pressure. And so what you have here is a partially evacuated glass cell, and light is coming in and hitting this structure with these vanes that spin. One side of the surface is dark and absorbing, the other side is shiny and highly reflective. And if radiation pressure was actually causing this to spin, it would exert more force on the reflective side. But in fact, as you can see, it's spinning the wrong direction. And the reason for this is that the residual gas that's in there is actually heating up from the dark surface, and you're creating a convection or current of the gas molecules is actually spinning it the wrong way. So Crookes, this was later discovered to be explanation. But in these optical traps, if you heat the surface of the nanoparticle, you can also get currents of these gas molecules, which can destabilize the trap. And so one needs to account for this. But it is possible to overcome this, essentially looking at ways of doing laser feedback cooling. So here's some earlier work we did studying this effect as a function of pressure. So this black line, let's just focus on the black line here, is the calculated radiometric force or photothermal force as a function of pressure going from the atmosphere down to the militar regime. You can see there's this sort of plateau where this force is staying constant over a wide range of pressures. At the same time, as you're removing the air, your gas damping coefficient is dropping. This force is constant, and so eventually you heat the center of mass temperature, and kick the particle out of the trap. And so the way to overcome this is to use some sort of feedback mechanism. And so the way we do that, and this is related to the question of how we observe the motion of the particle, it works in the following way. And so if you take our nanoparticle at the focus of the laser, basically we image the scattered light off of the particle onto a segmented photodetector. And so then by studying the relative intensity along the different segments, we can basically get a record of the position of the particle as a function of time. From this, we can determine the velocity, instantaneous velocity of the particle as a function of time. And then we can use that velocity signal to feed back the motion of the particle with a velocity-dependent force. And so this is done using acousto-optic modulators, where we basically can create a velocity-dependent damping to stabilize the particle. And this allows us to then get into this high vacuum regime where we have this sensitivity. You may be concerned. I was advertising this system as having very little friction and very little damping. And now I'm putting damping back into the system using the laser. It turns out what we're actually doing is cooling the temperature associated with the kinetic energy of the particle's motion at the same time as we're removing or reducing this mechanical quality factor. And so the force sensitivity actually depends on the ratio of those two. So it turns out with these schemes, you essentially are cooling the motion by the same amount that you're increasing the damping, so you don't actually spoil the force sensitivity that you would have had with the really high Q factor. And so then once you're in the high vacuum regime, we demonstrated that you could do force sensing at the zeptonewton level with these systems with sufficient averaging time. And we also did a force calibration using electric charge. So it turns out that 90% of the time with these particular particles, the particle has no electric charge. Occasionally you have one or two extra electrons on the particle. And so if you apply a known electric field with some electrodes, you can apply a known force. And from this, you can actually calibrate the force sensitivity. And so we showed you can, in fact, average down with the environment being quiet enough to actually see forces at this zeptonewton or 10⁻21 Newton scale. Yeah.
Does this allow you to measure forces in all directions or just in the direction of the laser beam?
Yeah, in all directions. I mean, so there's different options for different types of readout, for example. And the system I'll show in a moment involves an optical cavity standing wave trap. And so then you have enhanced readout sensitivity due to the finesse of the cavity. But in principle, you can measure all three directions if you can collect the light appropriately from different angles.
Okay, cool.
Yeah. So we want to use this sensitivity to consider looking for gravitational waves above the frequency band, where we've seen many now exciting discoveries over the past several years. And so the sources that we're looking for that we've been mainly thinking about are associated with dark matter. So I think one can argue dark matter has many things pointing to its existence. It seems to be about 5 times more abundant than the ordinary matter that we know about. And it's really one of the biggest hints, I think, that there's some sort of physics out there beyond the standard model. And so, in fact, 95% of the energy content of the universe is totally unknown to us. So it's certainly worthwhile to sort of explore this dark sector, so-called. If you look at dark matter, we really know very little about the mass of the dark matter constituents. So depending on the mass scale relative to, say, an electron volt, you can think about it as behaving sort of as individual particles. And below this, you can really think about it as behaving sort of a coherent background wave field. And so the candidates that we're looking for with our detector would be things like axions, which are constrained to be in sort of this mass range here, or in the much heavier side, we can look for things like primordial black holes, which could, depending on the mass, make up some fraction of the dark matter as well. And so,
excuse me,
yeah.
Why do you concentrate on that range?
Yeah, so these are examples where we've identified sources which can give signals that are in our sensitivity band within the frequency range that we're able to search well.
Okay.
So the
Sorry,
basic principle. Oh yeah.
So for the axion, you would be kind of looking for in a wave-like regime, right? But for the black holes, is the idea that, I don't know, a black hole flying by would exert a gravitational force on your particle, or what's the
No,
idea?
so we're really looking for like in spirals and mergers of kind of like subsolar mass primordial black holes, essentially.
So you're looking for the gravitational wave signal of that.
Yes. So all of the detections here are actually detecting the gravitational wave signature, either from the primordial black hole or the axion. And so Jacob in the talk after me is going to say quite a bit more in detail about some of the sources that we're looking at in a bit more detail. But let me just introduce the kind of the principle of the measurement for gravitational waves. So the idea is quite similar. You have some optical trap for a particle. In this case, rather than a single focused laser beam, we're using a standing wave trap like we do in several of our other experiments as well. So basically you have an optical cavity, and inside the optical cavity you have some standing wave, and you can trap a particle basically at any of the bright spots or antinodes where we have constructive interference along the standing wave, the length of the cavity. And so we can think about this as a gravitational wave detector. Really, I think it's quite a close analogy to the Weber bar or these resonant mass detectors in terms of the way it works. And so in this case, you have a gravitational wave of the right frequency causing this large massive object to basically ring like a bell. In this case, we have an optical cavity. And so we're considering a cavity much shorter, for example, than the LIGO-style detectors. So in particular, lengths ranging from, say, 1 meter to potentially up to 100 meters in the future. So the idea is that the gravitational wave will pass by the system. It'll change the physical distance between the mirrors. And what happens, so if you work in, say, for example, the local Lorentz frame of the input mirror, what happens is that the particle gets displaced relative to the antinode of the trapping field, which was confining it, as the mirror position oscillates due to the gravitational wave coming by. And so this basically creates a time-dependent force on the particle because you're displacing the potential from where the particle is sitting. And so it's really a resonant type detector in the same sense here, in that if this motion of the mirror occurs at the natural trapping resonance frequency of the particle, which is determined by the laser intensity gradient, essentially, then we can resonantly ring up the oscillation of the particle in this laser trap and study how it gets kicked around, essentially, from the gravitational wave. And so it's quite a bit more tunable than the bar detector, where the resonance is just set by the material properties. In our case, we can basically just turn the laser intensity, vary it by about an order of magnitude, and sweep over quite a significant amount of frequency range to adjust what band we're sensitive to. And so, for example, for numbers for about a 10-meter cavity, you can think about measuring strains at the level of 10⁻22 per root hertz at frequencies of order, say, 100 kilohertz. And so one of the key differences with using this approach as opposed to just sort of the LIGO type detectors to go to these frequencies is that in those detectors you tend to be limited at a high frequency due to laser shot noise. In our case, we're limited by this thermal Brownian motion of the particle, the same force I was mentioning earlier. And if you look at the frequency scaling, while the sensitivity due to the shot noise is getting worse at high frequency, our sensitivity is actually improving at high frequency due to the thermal noise. And so
why is laser shot noise not an issue here? Because also the trapping laser must be fluctuating, and that must wiggle the particle a little bit, right?
Yeah, so you can study the effect of, for example, like the radiation pressure shot noise from the laser trap itself. It turns out because you're sitting at the antinode, you're quadratically coupled only to that field, so it's not a very strong effect on it. But the direct displacement of the particle is actually accomplished with a second laser beam, which much lower intensity. But the basic idea is that because it's such a high Q resonant system, the actual displacement amplitude is quite large. So you're not limited in terms of your ability to measure how it's moving. You're limited by the other things that are kicking it around. For example, the thermal noise.
Which is a thermal noise coming from the residual gas in the cavity, or?
Yes, that's right. So there's still some amount of imperfect vacuum, which sets some limit. But in the limit where the vacuum is sufficiently good, then we're limited by this other quantum light scattering process that I mentioned from photon recoil heating.
But so it's the thermal noise in the particle itself, not in the mirrors. So
well, we actually care about that as well. But because we're at relatively high frequency, that's also something we have to pay attention to it, but we don't think that's the ultimate limit.
Is there any chance of making this whole thing cryogenic?
Yes, that would be good, but the budget probably needs a zero after it to make that work. So
that department
first we want to make it work at room temperature. But yeah, that would in principle improve it, absolutely.
Also briefly ask a question.
Yeah.
So at 100 kilohertz, you also don't expect to have any seismic noise of the mirrors influencing the system?
Very little, right? Yeah, because this frequency range drops off very quickly with frequency.
And at 100, and you have calculated that at 100 kilohertz, you don't need any seismic insulation anymore. So.
Yeah, very little. I mean, we're verifying that now with the prototype to sort of study the full spectrum of vibrational noise.
Okay,
but
thanks.
Yeah.
So at 10 kilohertz and a 10-meter cavity, your wavelength is much, much bigger than the size of the cavity, right?
Yeah, that's right. So in all the
aren't you just kind of moving the whole thing back and forth?
Yeah, so in the range that we're considering, it's still in the regime where the gravitational wavelength is longer than the instrument, similar to LIGO, right? So, so you can really think about the action on the mirrors as analogous to what the gravitational wave does for LIGO at its frequency band, right? So you're still changing the physical distance between the mirrors. And depending on what gauge you're using, the TT gauge, the mirrors don't move, and in the other gauge they do, but it's the same basic physics on the mirrors.
Excuse me, to get intuition, if you want gigahertz, what kind of cavity will you have to have?
So gigahertz I don't think is possible with this method. Maybe megahertz, so I'll say a bit more about that. Yeah, so because the laser intensity sets the frequency, and the particle would evaporate if you have it such tightly trapped. So yeah, so the vision then is to try to basically go above sort of where LIGO's sensitivity starts to diminish at sort of a few kilohertz to 10 kilohertz range, and potentially push up to the megahertz regime depending on how tightly we can trap these things. So Jacob is going to talk about the sources here in a moment. In particular, we're looking for these in-spirals of primordial black holes, or there's a process that he'll talk about in detail that's known as black hole superradiance, where you can basically have clouds of axion particles accumulating around spinning black holes, even within the Milky Way. And so the axion, being its own antiparticle, can annihilate and form a graviton. And so the graviton frequency, the gravitational wave frequency basically is twice the mass of the axion. And so for a gut scale axion, this turns out to be roughly around 100 kilohertz, which is in our sensitivity band. But I won't say too much more about that because the next talk will kind of go into that in some more detail. So let me just show the instrument development. So this is at an earlier stage of construction, showing basically the two vacuum arms of a Michelson interferometer with Fabry-Perot arms, similar to the miniature version of a LIGO, if you want. This is a picture looking at the input beam, the beam splitter, and the input mirrors of the two arm cavities here in the central chamber. And so right now we're working on commissioning first one arm of the detector, which hopefully will have some noise characterization curves on relatively soon here in the next upcoming months.
Sorry, can I ask a question?
Yeah.
You were showing a Fabry-Perot cavity before. Now is a Michelson? Or?
Yeah, so we still need to use two cavities to get basically common mode rejection, get rid of laser phase noise, and that sort of thing. And so we're still doing. You still benefit from having a second cavity as a comparison, right? So the effect is there for a single Fabry pearl cavity, but we basically study the relative effect on two cavities that are orthogonally oriented, just the same way that LIGO does, essentially.
So in one arm you will have a levitated particle and the other not?
Yeah, so we have a particle in each arm,
In
each arm, yeah.
But they will have different resonance frequencies then?
So you can adjust that with we have a beam splitter, which you can adjust the relative intensities to tune them to have the same frequency. Just by adjusting the relative splitting of the power between the sides.
Okay.
But yeah, good question. So it turns out to get the best sensitivity, you do better by having a particular geometry for the trapped particle rather than just having a spherical particle, for example. And so you really want a combination of a high mass, a high frequency, and low scattering due to this photon recoil process. So if you have a spherical particle, you have Rayleigh scattering, which is basically an isotropic scattering everywhere. This leads to a random kick from the photon recoil in any direction. If you have a plate or disk-like particle, you get primarily forwards and backwards scattering, which scatters light back into the cavity. So this leads to less randomness in that photon recoil heating process and reduces the noise from that. It also allows you to increase the mass while keeping the frequency very high, because you basically extend the size of the particle out radially while keeping it still fitting in one particular antinode of the trapping field along the laser beam. And so this gives you a very stiff potential for motion along the cavity. And we also have ideas and experiments to try to improve the mass by using multi-layer dielectric stacks of materials, for example, with different indices of refraction to get improved trapping frequencies as well as increased mass, and taking advantage of internal reflections in the material, but still in this sort of plate-like geometry. And so we've done some experimental work already verifying that this is possible. So here we're trapping these very high aspect ratio hexagonal prisms. So this is an example of some of the samples fabricated by our collaborator in Peter Pozowski's group in University of Washington. This has an aspect ratio of about 1 in 100. So it's 20 microns across, but only 200 nanometers thick. And so basically we shake these particles above our laser trap, and when they fall into the trap, they actually stand up where the face of the hexagon is along the laser axis. And then we can study the motion of the translational as well as these tipping and tilting angular modes of the particle in the trap. And so this geometry looks quite favorable in terms of sensitivity. For gravitational waves, you can have some figure of merit if you want. So this is sort of the strain limited sensitivity, both in terms of thermal noise and this photon recoil heating noise. And again, for the ideal sensor, you want a high mass, high frequency, as well as low scattering rate. And so there's two sort of regimes depending on what level of vacuum you're in. You're either in the thermal noise limited regime, which this figure of merit scale is like the square of the frequency, square root of mass times the density times the thickness. Or there's the recoil noise limited regime, which has a slightly different frequency scaling and dependence on the scattering rate. And so we can compare our plate-like structures with other state-of-the-art levitated nanoparticle experiments. And so you can see that for these plate-like geometries, we're already exceeding any other system that's been demonstrated so far, both in the thermal noise limited regime and in this photon recoil limited regime. So this looks, I think, quite promising, and we're trying to improve the mass of these things even by another order of magnitude in the near term. So the choice of material is deliberate. So this sodium yttrium fluoride material can be doped with rare earth ions. When you do that, you can actually do something called laser refrigeration, also known as solid-state laser cooling or anti-Stokes fluorescence cooling, where basically you can excite the material with light of a particular wavelength, and it tends to emit at a shorter wavelength, pulling energy out of phonons in the crystal. So this can be used to cool things down to sort of 100 Kelvin type temperatures in different materials. And so this, if we simultaneously trap the particle and cool the internal temperature of the particle, in principle, you could really crank the laser intensity quite a bit higher and potentially get to the megahertz regime at some point in the future. So this is something we're looking into. So depending on the size of the length of our cavity, whether it's 1 meter, 10 meter, or 100 meter, depending on whether we have different types of particles, a disk or a stack of multi-layer dielectric materials, for example, one can estimate the strain sensitivity as a function of frequency. Here, this is for a 1 meter instrument this is our target design sensitivity for our pilot instrument that we're building right now. And then we've done some estimates of possible sources that we're going to hear about here from things within the Milky Way. So let me just go ahead and wrap up this talk at this point. So we've shown that you can do calibrated sensing at the zeptonewton level with these levitated particles. We think this is promising for searching between 10 kilohertz up to a megahertz for gravitational waves. And we've been looking at geometric methods to improve sensitivity and get rid of effects due to recoil heating. And potentially in the future, we can get even higher frequency if we can get the solid state cooling to work. Most of our effort on source modeling has been looking at things like black hole superradiance, but we're very interested in other potential sources in this band as well. And then going forward, assuming we can reach our benchmark sensitivity levels, we're interested in developing a network that we're tentatively calling Golden, which would be the Gravitational Wave Observatory Levitated Detector Network. So Nancy Agarwal, who was formerly a postdoc in the group, is starting a new lab at UC Davis, and she's going to be planning on building a second node of the instrument there, as well as we have a collaborator at University College London who's interested in having one in Europe, and potentially in the future would be interested in having others join as well. So thanks for your attention.
Time for questions? Yeah.
So what kind of configuration would you use in order to measure the polarization of gravitational wave? Would you have two of these L's?
Yeah, so I mean,
far apart?
Exactly. So you could basically study how, depending on whether it's a cross or plus mode, the different particles would respond, depending on where, what direction the gravitational wave is coming in. So ideally, you'd want a few detectors so you could sort of figure out where the source was coming from, and then
How far apart should those detectors be?
Yeah, I mean, so so you'd want, so right now we have a baseline with the instrument that we're planning in California, pretty far from Chicago to California, but it'd be nice to have one, in the southern hemisphere eventually, and we have eventually one in Europe as well.
Yeah. Have you thought about trying to measure big G with the...
Yeah, so we have another experiment that I didn't talk about, which was actually the first experiment we were attempting with these levitated particles. We're trying to test the Newtonian gravitational inverse square law at very short distances by trapping one of these particles right up against a surface and then studying how it interacts with a mass that you bring nearby. This could, in principle, be used to calibrate this detector as well by having some sort of nearby gravitational interaction acting on the particle. But big G is difficult because you have to know very, very precisely the geometry of the particles and all the distance metrology very well and the density of the materials. So we're doing, I'd say, more of an inverse square law experiment as opposed to a big G experiment. But in principle, you could use this method for that if you had enough knowledge of the metrology.
Just a technical question: Is it easy to trap a disk, so rather than a sphere? A sphere sounds easier.
It turns out it's about the same, and we were pleasantly surprised by that, because if you think about it, when you release this thing, it's spinning, and we weren't sure it would find its way into the right configuration. But there is a stable minimum where it wants to stand up in the beam, and it seems to have no problem finding it, luckily. So, yeah.
So if I understand you correctly, the effect that you're looking for is coming from how the gravitational wave moves the mirrors, not the particle itself.
Correct. Yeah, there is also a displacement of the particle, but this is not so important.
So would there be could anything be gained by trapping not one but two particles and looking for relative motion of the two particles?
Yeah, actually, so assuming we get one particle to work, we're thinking about having more than one particle along the cavity, because if you consider the shape of the laser mode in the cavity, there's different positions with different intensities. And so you can basically study more than one frequency at a time, so kind of like a xylophone if you want to.
Yeah.
So if you had some sort of a chirping signal, you could excite different particles, or you could search multiple frequencies simultaneously, essentially for scanning for for monochromatic sources and things like that. But we haven't, yeah, we haven't had, I mean, apart from each particle in each cavity arm, we haven't considered kind of duplications of the same frequency in each arm. Right.
Thanks.
Yeah.
A question on this. So how broad could the band be?
Yeah, it's a good question. So it's about a part in 100. So the Q factor is really quite narrow. But if you look at our shot noise limited displacement sensitivity, we're estimating you can probably scan line widths of about a part in 100. So 100 kilohertz plus or minus a kilohertz, and then you can scan that around.
All right, let's thank Andrew again.